Yeah, let's move to the last one by Taylor Harvey from University of Florida. He is a third year PhD student. His talk will be on geometry effects in MCNP Palimi, simulation of a cube-shaped monolithic neutron scatter camera.
Great, thank you, Dr. He. I'll begin now. Like he said, I'm a third year PhD student in Dr. Andreas Engqvist's group at the University of Florida. We've seen a number of talks today already on neutron scatter cameras. So I won't belabor the point too much, explaining them the details of exactly how they work, but essentially they're a type of directional radiation detector that can reveal spatial information about neutron sources by extracting kinematic information from consecutive neutron scatters within volumes. So a major push in the design of a lot of the scatter cameras, including a lot of the ones we've seen today already, involved making them more compact and deployable for field applications, various things and safeguards. So our group at UF is designing a prototype neutron scatter camera that uses a single volume that will only make use of standard PMT photodetectors with the aims of making a detector that's both small enough for field deployment and is also relatively inexpensive. So while the simulation stage of this prototype, so primarily my research now is actually building and developing the prototype itself, but I've done a lot of MCMP simulations to kind of guide the design of the detector. And this presentation today will kind of focus on kind of a quirky subject that I've found while doing the simulations, and that's some geometric effects that we didn't necessarily anticipate at first. So a little bit on the relevance of just kind of directional neutron detectors in general. Safeguards, of course, uses technical and policy solutions to prevent the proliferation of nuclear weapons. And radiation detectors are a major part of this. A big scene right now, of course, is imaging directional detectors like Compton cameras for gamma sources and neutron scatter cameras, or time-coded apparatuses to gain special knowledge about source distributions and localization of those sources. And of course, as I mentioned, we want to make those systems portable and affordable so they can be deployed in a variety of field applications. So a little bit more on the kinematics. This has already been explained, like I said, several times today, but one thing I do want to point out here is the system I've been developing relies on a single organic scintillator volume rather than either optically or spatially separated separate volumes. So what that means is essentially I have a plastic scintillator cube that has a very, very fast light response. And instead of confining the scintillator pulses to different volumes, all of the light flashes essentially happen in the same volume. Now, the fast part of that is what's really relevant, where how we can pick out the difference between scatter 1 and scatter 2. So I'm using an EJ230 plastic scintillator, which is a fast timing scintillator. It has a full width half max of about 1.5 nanoseconds. So that's, you know, a lot faster than most other scintillators as far as timing. And that timing actually allows me to see if the timing between scatter 1 and scatter 2 is in the appropriate window. I can actually differentiate in the pulse stream what I believe to be a first neutron scatter and a second neutron scatter if it's in the right window. And essentially the cube is outfitted on each of its 6 sides with a PMT right now, photodetector. And the locations of the scatters are found, sorry, one second. Okay. The locations of the scatters are found by comparing the total light arriving at each of the photodetectors. So as Will actually mentioned in his presentation, where you had 2 photodetectors at the end of a still beam rod, the same kind of effect applies here, except there's 2 PMTs on each of the opposite sides of the cube, and the light arriving at each side of the PMT is used to localize in either the X, Y, and Z direction, and that happens all simultaneously with a scintillator pulse for scatter 1 and scatter 2. Once I find the positions of the scatters, you sum across all of the photoelectrons generated to find the energy deposition, and you also use time of flight between scatter 1 and scatter 2 to find the second scatter energy. And you can use these various kinematic factors to generate these back projected cones. While developing the simulations for this, we found some interesting things. And basically, when I say geometric effect, I mean that the imaging isn't quite the same in all directions. It actually depends on where the neutron source is with respect to the sides and the edges of the cube. So I'll go into that a little bit more. The simulation was done, like I said, in MCMP Polimi, and I've been using a custom MATLAB script for the kinematics and the cone back projection. You assume a kind of a infinitesimal or a arbitrary radius sphere surrounding the detector, and the back projected cones intersect with that sphere to form these images that you see here. This kind of gives you an idea of how an image is built up from a few cones to more cones down here. This is 1,000 cones, and this is just actually with 10 cones. And even with just a few cones, you can already see, kind of get an idea of the direction of the source, which is that red dot there. A little bit about imaging resolution. This is kind of needed to explain kind of the geometry effects later. Basically, to determine the imaging resolution, you just take these crosscuts of your image, whatever that may be. Essentially, a lower resolution is it's easier to find sources with a lower imaging resolution. And I've divided this separately into azimuthal and polar resolutions. So this is kind of what I mean by geometry effects. So here you see the detector cube. Now this detector cube in reality will have PMTs coupled to each of the 6 faces. But this is just kind of for ease of access. You can kind of see what the cube looks like. And I have I moved sources in this case from position 1. So this is normal to one of the faces of the detectors to position 4, which is normal to an edge of the detector here. So these source positions are represented by these 4 images. And so this is actually with no energy cutoff, deposition cutoff. Changing deposition cutoff will change the image. It'll make the cones more accurate, but this kind of blurs everything out and uses basically all the double scatters that are considered good. And as you see, just moving from position 1 to position 4 here, you do see kind of a change in the shape here, and that's reflected by the change in your polar resolution of each of these images. So as you notice also, the azimuthal resolution in this case actually doesn't really change all that much. It's kind of within error bounds, but the polar resolution changes quite a bit as you move from position 1 to position 4. So that's the first of these geometric effects. Now the second case, if you move the source kind of up in this curved arc towards a corner, and by the way, if you do this in any direction of the cube, you see the same results, it's just in a symmetric way. But essentially, if you move there, not only do you see a reduction in your resolution from a relatively good resolution to a relatively poor resolution, you also see kind of a change in the shape, the symmetry, the geometry of the images themselves. So you kind of go from this, if this was a perfect projection, this would be circular. And you move here and you kind of get this triangular odd shape here, which represents the source 7, which is normal to a corner of the detector. So that's kind of, when doing a variety of point source simulations with this detector, I noticed this effect, and I hadn't seen anything in the literature about it really, so I was kind of wondering about it. You see the same thing actually when you use a distributed source rather than a point source. These are some barrels filled with a spontaneous fissioning material, and this one's normal to a face, an edge, and a corner. Again, you see kind of a strange change in the imaging, and this is a lot of cones, by the way. This is like 10,000 cones, so this would probably be kind of a long measurement for this detector. But if you did it, you would see this change in both the shape and the resolution, both polar and azimuthal for both of these cases. And again, here I'll point out that the azimuthal resolution doesn't change too much when you just shift it around the detector azimuthally, but it does change when you kind of shift it in a polar direction, as in here. So a few things as to why I think this is. Of course, ideally, if you were to move a source around a detector, a neutron scatter camera, or if you move the scatter camera around itself, as the case would probably be in reality, you would want the image to be identical in all frames of reference. And it seems, at least with this design, that's not the case. So as the source has moved away from the normal vector coming from each of the faces of this cube, the imaging resolution tends to deteriorate. Pretty much, as far as I can tell, the best results you can get in the resolution is when it is normal to one of those faces, right? And the reason I think this decay occurs is because of sighting factors. Now, when I say sighting factor, I mean wherever the neutron scatters in the detector, it creates a scintillation event and light goes out in all directions. And of course, I use that light arriving at each of the photodetectors to localize where the scatter occurred, using a series of adjustments for gain and calibration curves that are done with empirical collimations along the sides of the detector. So the problem is different positions within the detector volume have different sighting factors to the PMTs themselves coupled to the side. So the cube I've been using isn't isn't covered the entire side of the detector. It's a round PMT 3-inch that's centered in each of the faces, but it doesn't outfit every portion of the sides. Because of this, some of the light is lost to the unoutfitted parts, interior faces of the cube, particularly at the corners and the edges. So if you think about it, if you imagine a neutron scatter event, a neutron moves into the cube, it scatters somewhere near, through a face, it scatters somewhere near that face. Each of the 6 PMTs coupled to each of the 6 faces is gonna see a lot of that light moving, it's gonna see a large percentage of the light. Whereas if you were to imagine a neutron entering the corner or the edge, a lot of the light is actually going to get lost in these unoutfitted areas of the cube. So generally, for example, you saw that the azimuthal resolution doesn't change as you move around the source around the azimuthal axis around the detector. Well, that's because you don't actually lose much light in either of the 4 PMTs around that axis. Basically, anywhere you enter, any neutron that enters the detector from one of these faces, you're gonna see more or less light from the 4 PMTs surrounding. Whereas if you have a neutron entering around a corner here, you're actually gonna lose a lot of the light in the polar direction from the 2Z PMTs when the first scatter event and the second scatter event as well happens close to these corners. And you see both of these directions decay when you move in the polar direction as well. Another thing to cover is the distortion, not only just the decay and the imaging resolution itself, but also this change in the shape that we saw here, for instance, where it kind of goes from a circular symmetry to almost more of a triangle. That's actually primarily what this image shows. There's kind of a bias where if you have a neutron coming towards a corner of the detector, it enters and scatters twice. Only the double scatters basically count. All the single scatter events are thrown out essentially. They're not useful for imaging. But when a neutron enters, it has to basically scatter inward. So it has this bias for it to be counted. And basically the scattering inward entering either of these 3 faces kind of cause a triangular bias sort of, and this kind of is illustrated by these 3 cones here. And these are kind of like an average cone generated when the neutron enters each of these. And you don't actually see that when your neutrons are moved through the face. So I've just called that scatter inward bias essentially. But basically all these effects should only appear in neutron scatter cameras or imagers that use this single volume design, basically where all the light scattering events happen in a single volume. I wouldn't expect any of this to affect optically separated systems. So it's sort of a unique quirk or bug to this design. And just going kind of from a simulation to what I'm actually doing now, I'm building the prototype based on the simulation results now. Currently it's in a 1D scatter camera. So basically it has 2 of the eventual 6 PMTs. And this is kind of a bigger, bulkier prototype version to what I ultimately want to make, which will be actually using the smaller 3-inch cube. But this is kind of the proof of concept phase. Right now I'm making a light curve for a neutron light curve for the EJ230 plastic, so I can actually find the proper neutron energy deposition, which is necessary for the kinematics. But then the next phase is to add 2D and 3D capabilities by adding these PMTs to the other sides of the detectors, fully characterize its efficiency, its imaging resolution, its spectroscopic capabilities, and test the point sources and distributed sources kind of similar to some of the simulation diagrams that I showed here. And design experiments may be similar to those in inspector scenarios or in search scenarios. And ultimately, the idea to fully compactify this source is to use a detector more at this size with the same concept, but using flat panel PMTs, which we have some of in the lab, which are basically the same as your standard PMTs. They're not actually SIPMs, but they have a much more compact form factor. And the hopes is to get that to kind of a both economical and a handheld size, or at least transportable size. Just a little bit about what a system like this could be ultimately used for. This has also been covered a little bit today, but you could use it for localization in limited search scenarios. The kind of typical example of this is if a container gets flagged at a border and you need to find a neutron emitting source somewhere in a limited area, that'd be very useful in that capability, as well as verification of warheads for treaty verification, the presence and movements of nuclear material in inspection scenarios, carried out by the IAEA, for example, wide area search and accidents or attack lost source scenarios, mapping neutron sources in contaminated enclosed spaces, and monitoring fuel. External imaging of reactor cores have been shown for some time-encoded imaging systems, so it could also analogously perhaps be used with scatter cameras, and image matching, shipping and receiving, and facility management. These are some of these things I've researched a bit during my internship at Brookhaven National Lab. And with that, I'd like to thank the MTV and CBT for funding, and as well as my advisor, Dr. Andreas Engqvist. And I will now take questions.
Thank you, Taylor, for your presentation. I see some questions posted on the chat, so I would read it to you. Would there be differences between simulation and measurements when looking at corners?
So there will be a number of, yes, there will be a number of things I'd expect. So one example is in the simulations I've done so far, I haven't considered any scatter of light. So basically I'm assuming that any light that occurs because of a simulation event that contacts any area that's not outfitted by a photodetector basically is killed, it's dead. We hope to kind of replicate this as close as possible with our actual detector, because we're going to use highly absorbing black material, not Banta black, but a similar material that is absorbing 99.99% of light, with the hopes of the idea is to reduce the amount of spread on the timing. I didn't even really go into that, but it's very important that we can actually see the secondary scatter, the second neutron. And if there's too much spread on the light arrival time, it kind of erases that feature. So eliminating that light is important. But as far as, I really am looking forward to seeing if these geometry effects, like you see here, are replicated.
The second question, I read it for you because I'm not exactly sure. You are plotting a spherical color map on a rectangular color map. What effect might this have on the shape of the point spread function as you move the point source? Any ideas on how to minimize the distortion from plotting?
Yeah, so as it said, it is a rectangular projection. I'm not exactly sure how to minimize. So in reality, for example, I'm sure if you can see my mouse, but this image right here, this is really a circular image. It is geometrical. It's around the point. Although the projection distorts it into this kind of oval shape, which I've actually just, because I've been looking at this so long, kind of got used to seeing this as basically circularly symmetric. But in reality, it is kind of a problem with projection. I don't, off the top of my head, know enough about projections from spherical to rectangular geometry to know how to reduce this, but
just for your reference, I remember our group, research group, we do the counter imaging and we plot this intensity map on a spherical, like a sphere. Then you use the color to represent the, like you're showing here.
Yeah, I have seen that animation before actually, and I do hope to finally, when I present all this research, my defense do want to look into how to make that animation myself.
Okay. Are there other groups? Are there other questions from the audience? You can post on chat or you can speak up on your microphone. If not, I have a general question, Taylor. My question is very general. Say, if I understand correctly, your research is try to use regular PMTs, which is non-position sensitive, and cover to the 6 faces of a single scintillation crystal. So have you done some analysis on how much sacrifice on performance if you compare with, because I know there's another big project funded by NA22 to Sandia and a number of national labs. I guess you are aware of that program. So my question is, if you use all the position sensitive photon sensors, like that very expensive system, compared with your simple one, how much performance in angular resolution would you sacrifice?
Yeah, that is a very good question. One of the goal really of this project is the mostly cost effectiveness and also secondarily portability. I definitely acknowledge that this method, the using opposite photodetectors, it does give poor imaging resolution results. So these resolutions you see here in 30 for azimuthal and around 20 maybe for polar are pretty typical of what I've seen for the simulation so far. And in a lot of cases, that's a lot worse resolution than many of the other systems. Of course, this changes if you use higher energy cutoff thresholds for energy deposition. If I only accept 2 MeV scatters, for instance, I get really good resolution, but those events are very rare, obviously, so I sacrifice efficiency, so there's that trade-off. The goal is, though, is to have a system that is rugged, compact, affordable, but not a highly accurate system. So a system that could be good for field deployment, but it's not going to be the most accurate system you can make. And hopefully the negatives of that are benefited by its relatively low cost.
Thank you. It's a good effort trying different alternatives. Are there other questions from the audience? Last call. If not, thank you, Taylor.